Alright, we are continuing with the video reading companion for Ghosh and Mallik, chapter 1, third video. So this is GM1c. We will look at page 29. That's where we are starting, chapter 1. The max number of hinges on one link in a constrained mechanism with n links. We will actually approach it differently. We will say let one link have I hinges and simple hinges, and then we will see how many links it must have for it to have 1 degree of freedom, constraint mechanism. So we will start like this. We will draw the link which has I hinges, and of course I am going to draw it with a finite number, but you can think of it as having some dashed component like this, and these hinges will be numbered. This entire thing is one body. It's easier for me to shade it like this, hatch it like this rather than put dots. The hinges are numbered, so this is hinge 1, 2, 3, 4, all the way to I minus 1 and I. Now these are connected to other hinges. Each of these hinges are connected to other links. So here's one link. This will be connected to one more, which we assume is here like this. The reason I am drawing it as a triangle is I want these hinges to be simple. So there's one more like this. One more like this. And so on, coming to this from somewhere, and then a single link here. And if we count these links now, so what we will say is the total number of links is n. See, this one has I hinges, right? So what is the total number of links? So we will go like this. We will say at each hinge there is one link, like this one, and then this one, and then this one, and so on. So that's I links plus this link itself, which is 1, plus the connecting link. So there is one between 1 and 2, one between 2 and 3, all the way to one between I minus 1 and I. So that is I minus 1. This is equal to 2I. This is the total number of links. This means I max is equal to n by 2. This is a basic thing that we just concluded from consideration of this picture. You can see, if you check the degrees of freedom, we have, if for 1 degree of freedom we require, let me come here, for 1 degree of freedom we require 2j minus 3n plus 4 equals 0. The number of joints, so what's the number of joints? We should check. So there's I over here, and then 1 and 2, so plus 2, and then for I minus 2 links there are 2, so plus 2 I minus 2. That's the total number of joints. This we multiply by 2, this 2 minus 3n but that we will, n is 2i, so minus 6i plus 4. Where do we stand? So here we have 2 minus 4, so that's minus 2 times 2 is minus 4, and that's 4, so that will cancel. And then here 2i and an I, that's 3i and 2 3i and 2, 6i minus 6i, so that is 0. So this has 1 degree of freedom, which we intuitively knew when we drew this picture. Okay, so that's the first part. We have I max is n by 2. That's an interesting conclusion. Okay, next panel. Constrained motion of a kinematic chain. Okay, so constrained motion of a kinematic chain of n links with simple hinges. Okay, still on page 29. All right. So now, what have we got? We have got 3n is equal to 2j plus 4. Why? Constrained motion, single degree of freedom. This we have got. Now let us say n is 4, right? So what is the minimum number of n, right? So we've got n2 is greater than equal to 4. The minimum number of links is 4, and so what we will say is, let's try a bigger number. Can we try 5? We come here and we realize, well, we can just look here, we can realize that we can't have 5. Okay, we can't have 5 because 3 times n is an even number, therefore n is even. So next, beyond n equals 4, we have n equals 6. So try n equals 6. Okay, I max is equal to n by 2, that is 3. So n is equal to n2 plus n3. More we can't have. We'll have binary links and ternary links, but for example we can't have any quaternary links. Okay, so that's the first thing. We also have this here. You see, we have 2j is equal to 3n minus 4. N is 6. We are trying n equals 6 now. So that's 18 minus 4 is 14. 2j is 14, so j is 7, right? 2j is equal to 14, right? This is also equal to the number of elements, as you may remember from the previous lecture. And so this number of elements is equal to 2n2 plus 3n3. And so this is 6, right? So we have two equations. n2 plus n3 is equal to 6, and 2n2 plus 3n3 is equal to 14. These are two simple linear equations. We can solve them, and what we find is n2 equals 4, n3 equals 2. That's it. So if we have 6 links in a kinematic chain, closed, constrained motion, right, single degree of freedom, and only simple hinges, in that case there are 4 binary links and 2 ternary links. Very good. Let's look at some possibilities. So there are 2 ternary links. That means here's one ternary link, here's another ternary link. Let's say the 2 ternary links are connected directly. Okay. Now I have 4 binary links. I could have one link on this side and 3 links on this side. But if I did, you see, if I have one link like this and 3 links like this, then this part just becomes one rigid body. So it's just a 4-bar mechanism. That's not interesting. So let me remove that, and let me say there are 2 on this side and 2 on this side. This has 1 degree of freedom. To see that it has 1 degree of freedom, you can fix this one, change this angle. This part is a 4-bar mechanism, so it has a single degree of freedom. This will tilt it this way to the new position, whatever that is. When you tilt it, this position will be taken, and then only this length and this length, you will draw 2 arcs, cut them, the position will be known. Okay, so if you think about it, you will realize that this does have 1 degree of freedom, as it should. Our entire prior analysis shows that. There is a good example of such a mechanism given in the book, and that mechanism looks like this. It has so this is a slider now. How did this happen? This happened by taking this hinge here to infinity. So let me show you. If I think of this part at infinity, right? I think of this hinge here, this hinge here. That's my big ternary link. That's this one. This hinge, sorry, it's here. This hinge is here. This hinge is here. This hinge has gone off all the way to infinity. All right, and then this link and this hinge, this link and this hinge. We use green here. From here to here, this one is here. This part is my other ternary link. This part is that ternary link, which is hinged here, here and here. This link is this link here, and this link is now, let me use blue here, the connection between this one and this one is the connection between this one and that far away hinge. And as this hinge goes off to infinity, the motion of this one is purely vertical. It is equivalent to a slider. We have done this in previous lectures, and you can see the same is happening here. This is figure 140A, and 140B has a different kinematic inversion. This has a different kinematic inversion of the same linkage, and you can think about it. All right, let's just wrap this up now. Instead of these two ternary links being directly connected, they could be separated also. So for example, we could have a situation where these ternary links are separated. They are connected through a binary link. Okay, so now there are 4 binary links. Here are my 2 ternary links. There are 4 binary links. If I put 1 here, then I have to put 2 here. I can't put all 3 there and connect this, because then it will become a rigid body. If I just connect this one to this one without an intervening link, then it will form a triangle. Okay, so it will be like this. let me point out with red. So this hinge and this hinge without the intervening binary link are here. This triangular base is now like this. This triangular, no, I'm sorry, this one, yeah, that base is there. This one through a binary link is connected. So this one through a binary link is connected here, and then something else will occur over here, you know, some long connection like this. But this part, and this part together, rigid triangle, it will just become one. So that's not interesting. This is interesting. Okay, so we will have this is the one that is shown in the book. Sorry. Okay, so this is 1.39b. Alright, what happens if we look for larger n? If we look for still larger n, n has to be even, so the next n is n equals 6. I'm sorry, 8. So the next n is n equals 8. So if I say n equals 8, this means that I max is equal to n by 2 is equal to 4. Therefore, n2 plus n3 plus n4 is equal to 8. Okay. Also, we keep going back to the same equation again and again, right? So we keep going back here. 3n is 2j plus 4, right? Or 2j is 3n minus 4. So we come back here and we say 2j equals 3n minus 4, which is 20. 2j is 20. This means 2n2 plus 3n3 plus 4n4 is equal to 20. n2 plus n3 plus n4 is 8, and this equation here. Now you see that I have two equations in three unknowns, and so you may think that there are infinitely many solutions, but in fact there aren't. That is because n2, n3 and n4 are non-negative integers, and n2 is at least 4. So if we come here, let us say we come here and we say try n2 is equal to 4. When we do that, when we put 4 here and here, we get two equations for n3 and n4, and we can solve them. So for example, we get n3 is 4. So let's try n2, n3, n4. If we put n2 is 4, we get n3 is 4 and n4 is 0. 8 links. Okay. If we try n2 is 5, then we get n3 is 2 and this one is 1. If we try n2 is 6, then we get n3 is 0 and this one is 2, and so on. Okay. Can we try 7? I suppose we could try. Is it possible to have 7? Let's try 7. If this is 7, here is a problem. If I say this is 7, then I have n3 plus n4 is equal to 1. And when this is 7, so that's 14. So 6, 3, n3 plus 4, n4 is equal to 6. But 3n3 plus 3n4, 3n3 plus 3n4 is equal to 3. Therefore, n4 is equal to 3. Okay, this means n3 is equal to minus 2. So that is not a reasonable solution. So there are no other solutions. Okay, this is the set of solutions, and the book says it is an exercise for you to think about the different mechanisms that can be drawn using these parameters. Before we proceed further, I want to do something. I want to discuss figure 1.41 and the problems associated. So now I'm going to look at figure 1.41. Okay. Now this has some linkages and you are asked to find degrees of freedom. This is problem 1.4, effective degrees of freedom for the mechanisms shown in figure 1.41. I just want to work through these with you so that you can get the hang of it. The detailed solutions are there in the book. One solution is incorrect. I will tell you which one that is. But first let us look at these. My intention is to offer you some kind of intuition. The equations are there in the book. You can follow that and I will not worry about those. I'm drawing it in slightly different shape, but it doesn't matter. Connectivity is important. This is one body. Now in the book the calculations show that the number of degrees of freedom is 1. I just want to show you why this is not surprising or why this may match your intuition. So I'll use blue now, and you will see that this being the fixed link and this is a 4-bar mechanism. It has 1 degree of freedom. This is a rigid body connected to the coupler link, so that has no additional degree of freedom. This by itself without contact is a 4-bar mechanism, so it has 1 degree of freedom, but we will move it until contact occurs, which is a scalar equation, right? Distance between these two is 0. You may find it difficult to write the equation, but in principle that equation can be written. It is a constraint, and so this also does not have additional degrees of freedom. The only degree of freedom you have is theta, so intuitively that is why this is a single degree of freedom. You can work out the equations. There is a higher pair there, so it is useful for you to study the solution. Okay, so this is problem A. Problem B looks like this. There is a ternary link here. This one comes here. There is a slider from here, again a connecting rod to a crank. How many degrees of freedom? So the book shows that the answer is 1 by calculation, but what I want you to see is I want you to look here and see this one is fixed, this one is fixed here, this one, and this one makes a 4-bar linkage, so it has 1 degree of freedom. Wherever you assign theta, accordingly this triangle is fixed, therefore this point is fixed. Then you know that you have to be a certain height above this. From this point, using this length, you draw an arc and it cuts in a unique place. Well, there's another faraway solution, but locally it is unique. So you know the location of this slider. Once you know the location of this slider and you know the location of this hinge point, you know this length and that, you draw one arc here, one arc here. Everything is determined. So this is the only degree of freedom, and you see that F equals 1. Okay. Now this one, this is problem B. Now let's do C. C is a little more interesting. Let's try some greenish color here. So C looks like this. How many degrees of freedom does this have? So the calculation shows f equals 3, but let's work it out. Now when I come here and I'll use red again, you see this whole thing is one link, right? So because it is one link and this is one link and this is fixed, so this is the this slider, that's a crank, so it's really a slider crank mechanism. It has 1 degree of freedom. If I assign some value to this hinge location is fixed, this length is fixed, right? Now I come here, I will return there, but let me come here. Over here, this is another degree of freedom. So over here, you know, I have assigned some theta. Over here, I assign some phi. Knowing this length, this is fixed, okay? But now this slider position, you see, in this slot is free. So over here, I will take this total distance to be L, and I'll take this distance to be L0, and this L is not known, but for any L, so I can assign theta, I can assign phi, then I can assign L, and after that, because I have assigned phi, this point is fixed. Because I have assigned theta, this point is fixed. Let me use blue. I have assigned theta, therefore this point is fixed. I have assigned phi, therefore this point is fixed. Now I have assigned L, therefore this distance is fixed. I draw an arc and I know L0, so this distance is fixed, and that fixes everything. So I am able to assign L, phi and theta. That is why f is 3. Okay, all right. Let's do more. Problem D, this was C. Problem D is a little problematic, it's a little difficult. What has happened is that the answer in the book is wrong. So, this is a slider, and then parallel to that is another plane. This is welded here. So I spoke to Professor Mallik about it. In the book, in the solution given, it is mentioned that since this can move without turning this one, therefore it is a redundant link. But actually that is not correct, because when this moves, this link moves and this link moves. It is not one link that moves without affecting anything else. So it is not a redundant link. And then when you see that it is not a redundant link, then you get f equals 1, as you should. The answer in the book says f equals 0. This is not correct. Okay? All right. The final problem is this one. It's a little complicated. I want you to think about it carefully. It is good for your intuition. Now this should be shaded. Sorry, dashed. Okay. So this is a parallelogram, right? This one and this one are parallel. Now the analysis in the answer, it shows that either you can eliminate this link or you can replace this one with a higher pair. So it's a slightly more complicated situation, but I think it is worth doing. Because of this slider and this one being rigid, this one stays vertical. Because this whole thing is one link and this one stays vertical, therefore this one stays horizontal. If this stays horizontal and then this link location and this link location are the same, in that case you see that this is redundant. So that part is easy. Okay. On the other hand, if these were both fixed, in that case over here you could just have a slide, you could have a higher pair contact over here and it wouldn't make a difference. Okay, but I'm not going to discuss this further. You can think about it more if you like. We now come to a really important topic, which is ranges of motion of a 4-bar linkage. Which is Grashof criterion. Now, if you are like me, by which I mean not terribly smart, then you will not be able to anticipate this, and yet it's a really wonderful result. So let me show you how it works. Now let's say I am working with a 4-bar linkage. Many mechanisms are 4-bar linkages. Now under this condition, let's say I want to drive one of these with a motor and make it go round and round. So I'm going to fix one of these and I want to know, can it complete a full revolution? Right? So this is clearly an important problem. It has practical implications. So we will study this, and the way we will do this is like this. We will say, I'll draw this linkage as follows. I'll say this is L1, this is L2, this is L3, this is L4. The reason I have drawn it like this will soon become clear. I am interested in the question of whether L2 can make a full revolution relative to L1. I will assume without loss of generality that L2 is bigger than L1, because it doesn't matter, right? Only the relative motion is important, and I will fix this L1. This is the one that we will study. Okay. So when we are studying this system, we have a bit of space here. So there are a few limiting situations that it needs to clear. Okay. So for example, if this is rotating this way, right, if L3 plus L4 is too short, then it will not be able to reach its full extent. So one of the configurations it has to reach is this configuration, L1, L2, and then this is L3 and L4, which means L1 plus L2 has to be less than L3 plus L4. Okay, but also when it is going all the way around, it has to be able to reach this position, and it may be stopped by that, right? So for example, you may find that L3 is very long and L4 is very short, and when that happens, then L3 goes off somewhere far away, and with L4 you can't come that close, so you will not be able to reach this position, right? So this other position that it has to reach is L1 like this, then L2 like this, and then maybe L4 like this, and L3 like this. Okay, how much is this distance? It is L2 minus L1. Okay, please forgive the imperfection in the drawing. This L4 and this L4 are supposed to be the same. Okay, so now what do we need? Now this triangle has to be possible. This means L4 has to be less than L3 plus L2 minus L1, which we write as L1 plus L4 is less than L2 plus L3. Okay, similarly this triangle has to be possible, so L3 has to be less than L4 plus L2 minus L1, which in blue works out to be L1 plus L3 is less than L2 plus L4. Okay, so these three inequalities, which I will now put in a red box, they govern the question of whether or not this link L2 will be able to make a full revolution with respect to L1. Alright. Now I may also be interested in whether L4 can make a revolution with respect to L1. And if I do that, then I get the same equations, except I should exchange L2 and L4. So if I exchange L2 and L4, this first inequality will become the second inequality, and the second inequality will become the first inequality, and the third inequality will not change. So L2 going round and L4 going round, same equations, same inequalities. Okay, but how about L3? Suppose I'm interested in whether L3 can go around, then there is a clever thing that we can do. We can look here. We'll look here. So here's what we'll do. There is this lovely bit of cleverness. We'll make a parallelogram over here, and this is L2, that's L3, this is L2, this length is L2, this length here dashed is L3. So now you can think, let me put L3 with an underline and L2 with an underline. Then I am interested in the linkage L1, L3 underline, L2 underline and L4, and I am interested in whether L3 can go around, right? And when I do this, then what has happened is L3 and L2 have been exchanged effectively in the equations. Let's exchange L3 and L2. So when I exchange L3 and L2, you see over here, if I exchange L3 and L2, then I get this one, and if I exchange L3 and L2, I get this one. If I exchange L3 and L2 here, nothing changes. And so with the same inequalities, I am able to guarantee that this link will go around this link. And now you will notice that by construction, this is a peculiar 6-link mechanism, but by construction, this is always a parallelogram. That means the angular position of this link and this link are the same. This is always parallel to that. L3 is always parallel to L3 underline. Therefore, if L3 underline makes a full revolution relative to L1, then L3 also makes a full revolution relative to L1. And that means that L3 making a full revolution also is just governed by these three inequalities. Okay, so these three inequalities govern the condition. They determine whether or not L2 or L3 or L4, any of them, is able to make a full revolution relative to L1. Okay, now here is something we can do. Let's take this inequality and this inequality and add them up. So we will get 2L1 plus L2 plus L4 is less than 2L3 plus L2 plus L4. Where did I get it? This one plus this one is 2L1. This one plus this one is L2 plus L4. Here this one plus this one is 2L3, and this one plus this one is L2 plus L4. And now I cancel L2 plus L4 and I find L1 is less than L3. Okay, I find that condition. And similarly, if I do the other one and the other pair, 3 pairs are possible. I find L1 is less than L2, L1 is less than L4. This means if S is the shortest link, then L1 is equal to S. Alright. Now we come here again to these inequalities and we say L1 is the shortest link here now, right? So now L1 plus L2 is less than the sum of the other two, L1 plus L3 is less than sum of the other two, L1 plus L4 is less than the sum of the other two. Now out of L2, L3 and L4, one is the longest possible link in the mechanism. Let that be just L. So then L1 plus the longest link is less than the sum of the other two. So let S, this is the shortest, and L be longest, and CD be other two links. And that's Grashoff's criterion. Use green here to liven things up a bit. So okay, the sum of the shortest plus the longest is less than the sum of the other two lengths. And this does not even require that the shortest and the longest are adjacent, right? So I can have the shortest here and the longest there, or I can have the shortest adjacent to the longest, and it doesn't matter, right? What matters is that the sum of the shortest length plus the longest length is less than the sum of the other two lengths. If that condition is satisfied, then full rotation is possible. Okay, otherwise it is not possible. So that's the Grashoff criterion, and you can see that it's really important. Okay, why is it important? So, well, let's look at this. Suppose let's suppose that this satisfies the Grashoff criterion. This is L, this is S, this is L, this is C, this is D. Okay. So this one will do a full revolution relative to this, but this one will then do a full revolution relative to that also. This one will do a full revolution relative to that also. Why? Because remember, we had fixed the shortest link in the other calculation. So L, C and D each does a full revolution relative to S. Conversely, S does a full revolution relative to C and D as well as L. So what happens here is this is a crank and that's a rocker. Okay, this is for Grashoff linkage. Non-Grashoff linkages have other possibilities, but full revolution is possible. Whenever we want to drive one link round and round using a motor, we want the linkage to be Grashoff. Alright, now we will think about a slider crank mechanism in the same connection in a few minutes, but you can see that all of those are important because the crank has to go round and round in a slider crank mechanism, and there are basic criteria that we need. Okay, now what happens if I fix this one? So if I fix the short link, Okay, let's just do that. So then this one and this one and this one all do full revolution relative to that. So this is the double crank. Similarly, if I fix that one, then I get something like this. And what will happen is this is the one that goes round and round, nothing else goes round and round when I fixed this. So this will rock, and that one will go round and round. There will be an intermediate position where this has come here, this has come there, and this link is, this has come here, then this will come down, this will go up. There will be positions like, well, there will be positions like this, for example. Okay, and there are intermediate positions where this one is vertical down, this one is up here somewhere, they'll be vertical. So this, we should see some animations of it to make it clearer for you, but there are basically both of these will just be rocking. That little coupler is the one that will be going round and round. So that will be called a double rocker arrangement. Okay, all right. Now, in the book, there are a lot of different examples given in figure 1.45. And I encourage you to look at those with care now that we have gone over the Grashof criterion with reasonable detail. But over here, I just want to do one more example. So let us say I have a slider crank mechanism. Okay. So let us say this is the crank radius L R, this is the connecting rod radius L. Do you think this will go round and round, or will it not? We should be able to do this using slider crank mechanism. So how will we do that? This link will go down to infinity. This link will also go down to infinity, right? Because this one is moving side by side. At infinity, this will meet. Let me draw it at an angle to indicate to you, but basically you think of it as very far away, then this is the 4-bar linkage, right? So if this hinge point goes to infinity, I think I have a bit more, no, I don't have space here. If this hinge point goes to infinity, then this will move horizontally. Okay, now this will be horizontal, which is longer. So let us say this offset is E. In that case, if that length is, L infinity, whatever it is, then the longest length is L infinity plus E. And then over here I have this R and I have this L. So I have whichever is the smallest, right? So I have the minimum of R and L, right, plus L plus E should be less than the maximum of R and, I'm sorry, not L plus E, L infinity plus E, R and L plus L infinity. And this is why the L infinity cancels, and this is our equation. So you see now, if I take the max of RL minus the min of RL, what do I get? this is nothing but the absolute value of R minus L, and that has to be greater than E. That's the condition for the slider crank mechanism derived from the Grashof criterion. I hope that is a useful example for you, and then you can study the rest of the examples in the book. There are some other technical details in the proof, so they are there in at the bottom of page 35. Okay, so if link 3 has to make a complete rotation with respect to either link 2 or 4, the angle has to exceed 180, but to exceed 180 it has to reach 180. To reach 180 it reaches an impossibility. That detail I have not covered, but if you read the book you will see that. And I will stop this lecture here. Thank you. This should come.